Today we're going to take a look at derivatives of trigonometric functions in section 3.4. But before we get started with the derivative of trigonometric functions, we need to recall a few things from section 2.3 on limits. If you recall from section 2.3, and you can refer to your notes for this, I did two very important limits. So let me kind of just write them down again and see if you remember. So we did two very important limits in that section. So it was a limit as x approaches 0 of sine x over x. And if you remember, I derived this limit for you and I told you what it was. But before I give you the answer, let's just remember a few things about this. Couple things. X goes to 0. X is the angle here. And the angle and the denominator are the same. So that's important. So the angle and the denominator are the same. Whenever that happens, if you take sine of x divided by x, where the angle and the denominator are the same and the angle goes to 0, then that limit is always 1. And then the second limit that I did for you was this one, limit as x goes to 0, we get cosine of x minus 1 over x. Okay. Now, this limit, if you think about it, it is cosine of 0 is 1, 1 minus 1 is 0 over 0, so you'll have to do some math over here to figure this limit out. And if you refer to your notes from section 2.3, you'll notice that we found this limit to be 0. So these are the two limits that we're going to use today when we talk about derivatives of trigonometric functions. Okay. Again, if you don't remember this, please take a few minutes and just go back and look through your notes for section 2.3 before you proceed. Okay, just pause the video and go back and look at it. So let's get started. So the first thing we're going to do is find the derivative of y is equal to cosine x. We're going to start by finding the derivative of cosine x. Now, anytime you find the derivative for the very first time, if there isn't a formula for that, or if you don't know the formula for that, you use the formal definition of derivatives. So the formal definition of derivatives is this. And you've seen this definition many times before, but it's called the formal definition of derivatives. And anytime you derive the derivative for the very first time of a new function whose derivative you do not know, then you always use this to help you with that, which is f of x plus h minus f of x divided by h. It's basically the limit of the difference quotient. Okay, so we're going to use this formal definition to find the derivative of cosine x. All right, so let's do that. So f of x plus h, my function here is cosine x. I'm going to replace x with x plus h. So I get the limit as h goes to 0. I get cosine of x plus h minus cosine x divided by h. You can convince yourself that as h goes to 0, this term will go away with 0. You'll get cosine of x minus cosine of x, that's 0 over 0. So this is a bad thing, we know that. We've talked about that many times in class. So what do? With algebraic problems, we either simplify, rationalize, or factor. But this is trig. So with trig problems, you basically do two things when you're working with limits with trig problems. You can still factor and simplify and things like that, but with trig problems usually you'll end up using one of these limits, probably this one more so, and you can always use trig identities to help you along. Okay, so with trig problems you have more things to leverage. You can still do the factoring, simplifying, and all of that with trig problems, but you can also use trig identities, and you can also use the two limits that I told you about earlier. So if you recall, there's a trig identity for cosine of x plus h, cosine of sum of two angles. Okay, I have given this to you in section 1.3. So you can again go back and look at that, which tells you cosine of x plus h is cosine of x, cosine of h. Actually, I should really write it the way I gave you in class. So I called it cosine of a plus b, sum of two angles, which is equal to cosine of a, cosine of b minus sine of A sine of B. So that's the one we're going to use, except in our case we have x for A and h for B. So let's do that. So we have, as h goes to 0, we have cosine of x cosine of h minus sine of x sine of h minus cosine of x. Divide that whole thing by h. It's still 0 over 0, but we're making progress, and now we're going to simplify a little bit. Okay, if you notice, there are a couple things that are nice here. In this term and in this term, I have cosine common, so I can combine those two terms. And if you remember from the limit laws, what do we say? If you take limit of f plus g, what does that mean? You can take the limit of f plus the limit of g term by term. And there was another limit law that we talked about. If you take the limit of a constant times a function, what can you do with the constant? You can pull it out. So we get that. So these are the two things we're going to use here. Okay. All right. So first thing I'm going to do is I'm going to combine those two things that I've underlined and factor out a cosine. So I get cosine of x times cosine of h minus 1. Just look at these two things here. I took out a cosine. I got cosine of h. And when I took this cosine out, I get a 1. I'm going to divide that by h because I'm dividing that by h minus I have sine of x sine of h divided by h. So I have this term here. And I just split this up. If you find the common denominator, you'll get exactly this back. So I didn't do any magical stuff here. It's the same thing. Now, I'm taking limit with respect to h. So anything that doesn't have an h in it becomes a constant. So if you look at this, this is a constant, so I can pull it out. So I'm going to do that. So I get cosine of x limit as h goes to 0. I get cosine of h minus 1 over h minus, I'm going to go ahead and distribute this limit here. That's what I'm doing, term by term that I just talked about. Once again, this has nothing to do with h, so I can take this sine x out. I get the limit as h goes to 0, sine h over h. Now, this limit here and this limit here were the two limits that I talked to you about earlier. Okay, we found that this limit was identically equal to 1, and we found that this limit was 0. So this will become 0. Because this limit is 0, this whole expression here will be 0. And since this limit is 1, sine x times 1 is just sine x, and there's a negative here, so you get minus sine x. So it tells us that the derivative, okay, so that gives us a first formula for trig functions. We just learned that the derivative of cosine x is equal to negative sine x. And these formulas, you absolutely have to memorize. There's no way around them. So just start creating flashcards or whatever that you can do to help you with the memorization. So once again, derivative of cosine x is negative sine x. All right. Now, next thing we're going to do is find the derivative of sine x. Now, I could do exactly the same thing that I did here. Okay, you can follow the same steps, except instead of using this identity, you would use the identity for sine of the sum of two angles, and you would get you can follow it step by step, and you'll come up with the derivative of sine x. But just to be different, I'll do this problem differently. Okay, so I know that sine function looks like this. It goes up, down. So this is 0, pi, 2 pi. This point here is 3 pi over 2, and this is pi over 2. So this is a graph of the sine function. This is 1 minus 1. Now, I showed you in class, if you're given a function, like I said, this is a graph of sine function, you can use the concept of the concept that the derivative is just the slope of the tangent line. You can use that idea to graph the derivative given the function. So that's what I'm going to do here. But before I do that, I just want to point out a couple things. There are a couple special points over here. So let me point those out to you with a different color. This is a special point because if you were to draw a tangent here, you'd notice it's exactly diagonal. If it's a diagonal tangent, that means the slope is 1. Okay. Same thing over here. If I had drawn this function correctly, if I were to draw a tangent here, it'll be exactly diagonal and the slope would be 1. Same thing over here, the slope would be 1. So I have 3 special points that I know of, and at those points the slope is 1, positive 1. Out here it's negative 1 since it's going diagonally down at 45 degrees, and out here it's positive 1. So let's do that. So the derivative at 0 is going to be 1. Okay. Derivative at pi is going to be minus 1 because the slope of the tangent line at pi is diagonally and it's going negative, so it's minus 1. And the derivative at 2 pi is 1. Okay. So those are the 3 special points that I told you about, but there's 2 more. So let's take a look at those 2. That's this one. Okay. At pi over 2, you notice if you were to draw a tangent, what is the derivative? 0. At 3 pi over 2, if you were to draw a tangent, the derivative would be what? 0. Why is that? Because derivative is the slope of the tangent line, and the slope of the tangent line out here is what? 0. Okay. So that's why the derivative is 0. So at pi over 2, the derivative is 0. So this point will be right here. Okay. At 3 pi over 2, the derivative is also 0. So it'll be right here. Now if you connect these yellow dots with a smooth curve, you would end up with this. What does that remind you of, the yellow curve? So the blue curve, let me do that, use a different color. The blue curve, I'm sorry, I'll draw it in blue. The blue curve is the sine graph, okay? Okay. And the yellow curve is the derivative of that, which if you know your graphs of trig functions, you'll recognize that that is just the graph of cosine x. So that just happens to be the graph of cosine x. So that's really cool because we just figured that out. We figured out that the derivative of sine x is just cosine x. We did not use the formal definition or anything. All we did is use the concept that the derivative is just the slope of the tangent line. So we tried to find the slope of the tangent line at a couple special points here on the sine graph and connected those points and recognized that that was the graph of the cosine function. So that tells me that the derivative of sine x is cosine x. Once again, you could have found this using the formal definition. You could have gone through the same steps that I did before for the cosine, derivative of cosine, all these steps using sine. But this was something different, so hopefully you understand it. And if you don't, you can always use the formal definition, right? Now that we know the 2 derivatives of cosine and sine, what about the derivatives of other trig functions? So let's take a look at those derivatives of other trig functions. Okay. Well, I will do 2 of them and I'll give you 2 of them, the other 2 for homework. So now let's start with the y is equal to tangent x. Okay, I want to find the derivative of this. Now you can use the formal definition to do it, just like we did with the cosine at the beginning, but we know that tangent is the same thing as sine x over cosine x, and this is a quotient. Okay, and we know the derivative of sine and cosine now, so we can just use the quotient rule and figure out the derivative of tangent x. So let's do that. So I'll take the derivative applying the quotient rule. So if you recall, quotient rule tells us what? Take the derivative of the top, derivative of sine is cosine, times the bottom, minus the top times the derivative of the bottom, which is negative, if you recall, sine x, derivative of cosine is negative sine x, divided by the square of the denominator. So now if you simplify, cosine times cosine is cosine squared x. This negative and negative will become a positive. You'll get sine squared x over cosine squared x. We know from trig the identity cosine squared plus sine squared is 1. So we get 1 over cosine squared x. So this is 1. This is an identity from trig. So now we know that another way to write, because we know 1 over cosine is secant x. So this will give us secant squared x because you have cosine squared. So that gives us a new formula. Derivative of tangent x is secant squared x. So this time we didn't use the formal definition. We just wrote tangent as sine over cosine and then we use quotient rule. Alright, so we did that. Let's do the same thing to find the derivative of secant x. So let's say if you're given y is equal to secant x, which is the same as 1 over cosine x. Okay, this is a quotient again, so let's use quotient rule. So we take the derivative of the top, derivative of a constant is 0, times the bottom, minus the top, which is 1, times the derivative of the bottom, which is negative sine x, because derivative of cosine is negative sine, divided by cosine squared x, the square of the bottom. This 0 times cosine x is 0, so that's gone. So we get this negative and negative will become positive, so we'll get sine x over cosine squared x. Now we need to clean this up a little bit to make it look nicer, so I'm just going to write it a little bit differently and you can verify this. I have sine x over cosine x times 1 over cosine x. If you multiply these cosines, you'll get cosine squared, and sine x times 1 is just sine x. The reason for doing this is because this gives us tangent x times secant x. If you recall, there's an identity in trig that says that tangent squared x plus 1 is equal to secant squared x. So basically, tangents and secants always go hand in hand, they go together. So we always want to write the derivative of tangent using tangent and secant, just like we did over here. This would have been a perfectly good answer for the derivative of tangent x, but we always want to write derivative tangents and secants together. So we wrote 1 over cosine squared as secant squared. And same reason for that, same for doing it over here. So that gives us that the derivative of tangent x, of secant x, is equal to tangent x times secant x. So that's your next formula. Now all of these formulas you can find in the front cover of your textbook, so if you ever forget them and you need them really quickly, you can look at the front cover of your book. 3 y is equal to cotangent x, and 4 y is equal to cosecant x. Now these I want you to do for homework, just like I did the tangent and the secant. I will collect these during the next lecture, so make sure you have them done. So you need to do these for homework. I will give you the answers for these though. The derivative of cotangent x is equal to negative cosecant squared x, and the derivative of cosecant x is negative cosecant x cotangent x. So I've given you the answers, but you need to show me all the work, how we come up with these formulas. It's important to learn how the formulas come about, so if you ever forget them, you can always do them on your own and figure them out. Now that we know the new derivatives, let's see what how we can find some of these other, how we can find the derivatives of more complicated functions. Okay, so let's take a look at that. So let's say if I give you this example, I give you y is equal to cosine x over 1 minus sine x. And I ask you to find y prime. This is a quotient, so we'll have to use quotient rule, so let's do that. So we take the derivative of the top, derivative of cosine is negative sine, times the bottom, 1 minus sine x, minus the top, times the derivative of the bottom, derivative of 1 is 0, and derivative of sine is cosine, but there's a negative in the front there, so it will be negative cosine this time. Okay, and divided by 1 minus sine x squared. Okay, so now let's clean up our derivatives. We always want to clean up our derivatives. So I'm going to go ahead and distribute here. So you get negative sine x plus sine squared x. I'll distribute here. We get plus cosine squared x divided by 1 minus sine x squared. Once again, from trig, we know that sine squared plus cosine squared is 1. So we get minus sine x plus 1 over 1 minus sine x squared. If you look at the top term, which is really, if you rearrange it, it looks like this. Oops. If you put the 1 in the front, you get this, which is exactly what we have on the bottom, so we can cancel one of these. This becomes a 1. So we get 1 over 1 minus sine x. So that is a derivative of that function. Okay. So we can apply the same product rule, quotient rule like we did before to these trig functions. Okay, let's do some more examples. Let's say that if I give you y is equal to tangent squared x, and I want to find y prime. Now keep in mind, this is a composite function. We have an outside function and then we have an inside, and we don't know how to do that yet. So we just need to be creative in terms of how we write tangent squared. I can write tangent squared as tangent x times tangent x. And now I can go ahead and take the derivative, but this time I'll have to use product rule. So let's do that. Derivative of tangent is secant squared x times tangent x plus the first, which happens to be tangent, times the derivative of the second, which is also secant squared x. Okay. If you notice, I have 2 of these, so I can add them up. So I get 2 tangent x times secant squared x. That is your answer for that. Okay. And we can continue to do all kinds of problems with this. I'll do one more and then we'll call it quits here. Okay. So let's say if you have y is equal to, okay, let's say we have secant x divided by, actually let's do 1 plus secant x. Okay, let's do 1 minus secant x on the top divided by 1 plus secant x. Find y prime. So let's start. This is a quotient, so we'll have to start with the quotient rule. So the derivative of the top, derivative of 1 is 0, derivative of secant is secant tangent. You get secant x tangent x. You can refer to the formula that I gave you earlier, times the bottom minus the top times the derivative of the bottom. Derivative of 1 is 0 and derivative of secant is secant x tangent x. Secant tangent is all we call that. Divided by the square of the denominator. And just like as always, we need to clean up our derivatives, so we'll distribute here. So we get minus secant x tangent x minus secant squared x tangent x. I distributed this. Do the same thing out here. I'll distribute this. Keep in mind though there's a negative in the front, so be careful. Minus secant x tangent x plus secant squared x tangent x. That's plus because of the negative. And in the denominator we still have this. So if you notice, I have a minus secant squared x tangent x and a plus secant squared x tangent x. They cancel. The others get doubled because there's 2 secant x tangent x, 2 of them. I have 2 of these, and divided by this, and there's your answer. So this is y prime. Okay. All right. How about this example? Find the equation of the tangent line, okay, to the curve y is equal to 3 plus sine x at x is equal to 3 pi over 2. Okay, so at that point. Alright, so the first thing is, anytime you want to find the equation of the tangent line, or any line for that matter, tangent line, we need what? We need slope and the point. So let's see. They've given us the x value of the point, but they haven't given us the y value. But that's easy. I can take this x and plug it in here to find the y. So let's do that. So if x is equal to 3 pi over 2, this tells us that y is equal to 3 plus sine of 3 pi over 2. If you know your nice angles, you know that sine of 3 pi over 2 is minus 1. So you get y is equal to 2. So from here we can extrapolate that the point is 3 pi over 2 and 2. So that's a point where we want to find the equation of the tangent line. So we have the point, now we need the slope. But that's easy also because we know that the slope of the tangent line is the same as the derivative. So let's just find the derivative of this function. Derivative of the constant is 0 and derivative of sine is cosine, so we just get cosine x. So that is my slope. I want to find the slope at x is equal to 3 pi over 2 because that's the value that we have. So we get this is equal to cosine of 3 pi over 2. Again, if you know your nice angles, you know that cosine of 3 pi over 2 is 0. So that tells me that the slope is 0. If the slope is 0, then the tangent line must be horizontal. And if it's horizontal, it must go through the y value of that point, right? Just 1 second. Okay. So let's figure out. All right. So I want to find the equation of the tangent line. It's y is equal to m times x minus x1 plus y1. The slope is 0, so we get x minus 3 pi over 2 plus 2, because that's a point. So we get y is equal to just 2. And you could have just figured that out by knowing the fact that since the slope is 0, the tangent is horizontal, so it must go through that point. The point was, that was this point, so it must go through y is equal to 2. Alright, so that's the answer to that question. And you'll see the same types of problems that we've done before. Okay. Now, here's a interesting derivative. So let me go ahead and do this problem. Let's say you have f of x is equal to sine of minus x plus cosine of minus x. And we want to find f prime of x, the derivative. Now, this is a composite function because normal function would look like this, sine of x. As soon as you change x, it's something different. So it's a composite function. We changed x. So we don't know how to find this derivative because we don't know chain rule. Chain rule helps you take derivatives of composite functions. So for now, I need to rewrite this without this being a composite function. So you recall from section 1.3 that sine is an odd function. So sine of minus x is negative sine x. And cosine is an even function. So cosine of minus x is cosine x. If you remember that from section 1.3. So this function can be written as negative sine x plus cosine x using this fact. Okay, so now that we have that, we can take the derivative. We know the derivative of sine is cosine, but there's a negative in the front, so we'll have to carry that, cosine x. Derivative of cosine is negative sine, so this positive will become a negative. So we get that. Okay, so you can see that we can take derivatives of functions like this if you recall the fact that they're odd and even. How about this example? Okay. They've given you find the slope of the tangent line to the curve y is equal to x sine x at the point pi over 2, okay, and pi over 2. This time they didn't ask us to find the equation of the tangent line, they just want us to find the slope of the tangent line. So that's not too bad. We know that the slope of the tangent line is the same thing as the derivative. Okay, well, the derivative. So let's take the derivative of this function that's given to us. Remember, this will require a product rule because this is a product. So let's do the product rule. So we take the derivative of the first, which is 1 times the second, plus the first times the derivative of the second. Derivative of sine is cosine. Okay, so we end up with sine x plus, my pen is acting really weird today, cosine x. So now we want to find this derivative when x is equal to pi over 2, because that's where we want to find the derivative. So the slope, sorry, which is the derivative, so that's okay. So we get sine of pi over 2 plus pi over 2 times cosine of pi over 2. If you know your nice angles, cosine of pi over 2 is 0 and sine of pi over 2 is 1, so this tells me that the slope of the tangent line is 1. Okay, I think I'll do maybe one more problem or two more problems and we'll be done. Okay, so they want you to find all values of x between 0 and 2 pi, okay, for which the curve y is equal to sine x minus cosine x has a horizontal tangent. Okay, so if you were to graph this function, you'll notice that it goes up and down, and there's many places where the tangent is horizontal. So you want to find those the x values of those points, just the x values. We are not looking for the point, just the x values. Okay, so let's do that. We know what if the tangent is horizontal, what do we know? The slope must be what? 0. We know that. Okay, we also know that the slope of the tangent line is just the derivative. So let's find the derivative of this function. Derivative of sine is cosine, and derivative of cosine is negative sine, but remember there's a negative in the front, so this will become a positive sine. And this should equal to 0 because the slope of the tangent line is 0. I'm going to solve this for x. There's a couple different ways you can do this. You can square both sides and do this problem. But this is a trig equation. You can see we have an equality and trig function. So if you recall, we always want to make our angles the same, which they are. So that's a good thing. Next thing, we want to try to make the trig functions the same if you have squares. I don't have any squares, so I can't do that. And then we abbreviate and solve. So in this case, that's not going to help us. And I told you the method that I gave you in section 1.3 works for about 90% of the problem. Every once in a while, you'll get a problem where you'll have to think outside the box. And this is one of them. So the way you tackle this problem is, like I said, one way to solve this problem is square both sides and do it, and that'll work perfectly fine. But another way to do this problem is I'm going to move the sine term to one side and the cosine term to the opposite side. Okay. Then I'm going to divide both sides by cosine x. So I'll end up with minus 1. Now I can only legally do this step if I can say that cosine x is not equal to 0. If cosine x is equal to 0, I cannot divide both sides by cosine x. That will be division by 0. Now, when is cosine x 0? Just for a second, imagine you didn't have that. Cosine is 0 when x is pi over 2. So we can say x cannot be pi over 2 and 3 pi over 2. These are your nice angles. We know that cosine of pi over 2 is 0 and cosine of 3 pi over 2 is 0. And we said cosine x cannot be 0, so x cannot be these values. If x is one of these, then cosine of that angle would be 0. All right. So this is important because if we end up with an answer of pi over 2 or 3 pi over 2, those cannot be our answers. Okay? All right. So now that we have that, sine over cosine is tangent x. Okay? So that's nice because we solved our equation. Now we want to find out what tangent of what angle is negative 1. So minus 1 means that tangent is coming out of quadrants 2 and 4. And the reference angle, remember when we do reference angle, we don't care about the sign. So ask yourself, what would happen if I hide the sign? Tangent of what angle is 1, which would be pi over 4. Again, these are your nice angles. In the second quadrant, we'll get x will be 3 pi over 4. You can convince yourself if you draw a picture. Here is my reference angle, pi over 4. So this angle out here would be pi minus pi over 4, which would give you 3 pi over 4. And in the fourth quadrant, you'll get 7 pi over 4. And those are both valid answers in our range. They wanted the answer between 0 and 2 pi, so those are both in our range. And we didn't get pi over 2 or 3 pi over 2, so we don't need to worry about that. So these are your answers to that problem. Okay, and you can always graph these functions to see if they are actually your answers. Okay, so let me show you that, how to do that. Okay, second. So you can, one of the things is you really need to use your calculators to the best of your ability here. Okay. All right. So if you want to check the answer, the first thing I'm going to do is I'm going to make sure my mode is in radians, which it is, and I'm going to make sure I'm plotting functions. Okay. I'm going to go to y equal to clear everything. And I'm going to type my function, the function I started with. If you recall, what was it? It was cosine x plus sine x. So let's graph that. So we have cosine x plus sine x. And I'm going to change the window. I'm just going to go from 0 to 2 pi. And I am going, y min is just going to be, I'll leave it as negative 3 to 3. And I'll go ahead and graph it. Okay, so there's your function. And I got two answers. The answers were 3 pi over 4 and 7 pi over 4. So let's check them. If you notice that you have here the trace key, if you press second and the trace key, you have all these options. Okay, so we can find the zeros, we can find the values, we can find the derivative and so on, and integral and so on. So I'm going to pick derivative. And now it's looking for the x value, so we can go 3, no, it was a 3 pi over 4, right? 3 pi divided by 4 and press enter. Okay, and it tells us that the derivative there is that, and that is not right. So let me go back and check my answers. Let me check my function that I started with. It was 3 pi over 4, right? Oh, I was graphing x minus, sine minus cosine x, okay? So I graphed the wrong function. So let me go back and do that again. So I'll go back and it is sine x, so I'll delete this. Sine x minus cosine x. And we can graph it. So let's go back to a second and trace 6 for the derivative, and let's just type in the value 3 pi divided by 4. Now this should give us derivative of 0, so let's check that, and which is correct, and it shows us that's where it would be. Let's try it again. Trace 6 for derivative, type in 7 pi divided by 4, and you can check that too, and the derivative is 0. So you can always use your calculators to check your answers, okay? All right. And the last problem that I'm going to do in this section is this one. We want to find all points on the curve y is equal to 1 plus 2 cosine x, where the tangent line is perpendicular to y is equal to 1 over square root of 3x plus 1. So we want to find all points. So just let's pretend that the curve looks like this, that some curve y is equal to 1 plus 2 cosine x. On this curve, there are some points where if I were to draw a tangent, oops, that's the wrong one. I'm not doing horizontal tangent. Okay, so let me draw the curve sideways. That'll be easier. So I have some curve like this. If I were to draw a tangent on this curve, which is this that I've drawn, it's going to be perpendicular to this line. Okay, so let's pretend that that line is like this. This is the line. Okay, this is my line L, which is y is equal to 1 square root of 3x plus 1. Now they're saying that if you were to draw a tangent on this curve, like for example, if I were to draw a tangent right here somewhere, you'll notice that that tangent intersects that line. So this is my tangent. They want us to find this point. Same thing out here. If I were to draw a tangent here, it intersects at 90 degrees. It's perpendicular. So I'm looking for these points where the tangent intersects the line that's given to me at 90 degrees. Since we're talking about tangent line, let's first find the slope of the tangent line. So let's do that, which is given by the derivative. We know that the slope of the tangent line is that. Okay. So let's take the derivative of this function. Derivative of 1 is 0. Derivative of cosine is negative sine, so I get negative 2 sine x. Remember, derivative of cosine is negative sine. So here's my slope of the tangent line. Okay. I know the slope of this line. The slope of this line is 1 over square root of 3. Okay. What is the relationship with this slope and this slope? Because they are perpendicular, we know what? Slope of the tangent line is equal to negative 1 over the slope of the line because they're perpendicular. So let's plug them in. So this mt would be negative 2 sine x is equal to negative 1 over ml, which is 1 over square root of 3. So you get negative 2 sine x is equal to negative square root of 3 when this flips and goes to the top. So we get sine x is equal to square root of 3 over 2. Okay. So now we just need to solve for x. We want to find out for what x is sine of x equal to square root of 3 over 2. Since this is positive, sine is positive in quadrants 1 and 2. And then the reference angle is pi over 360 degrees. Okay. In the first quadrant, the reference angle and the angle are always the same, so we get pi over 3. And in the second quadrant, the angle is pi over 3, so it'll be pi minus pi over 3, so it'll be 2 pi over 3. They wanted us to find, what did they want? All points. So we found the x values. Okay, now technically these are not all the points. If you really truly wanted to find all the points, it will be this plus 2 n pi, 2 n pi if you recall. And then the other one would be x is equal to 2 pi over 3 plus 2 n pi. Why is that? Because sine is periodic every 2 pi, so we do need that. So technically this is the wrong answer, this is the right answer. But again, this is not the answer either, so I apologize. They wanted us to find the point. This is just the x value of the point. So let's find the y value of the point. Y is equal to, if you recall, was 1 plus 2 cosine x. So it's equal to 1 plus 2 cosine of pi over 3 plus 2 n pi. And out here, so we get 1 plus 2. Cosine of pi over 3 plus 2 n pi would be the same as cosine of pi over 3 because cosine will wrap around and come back to the same point. So cosine of pi over 3 is 1/2, so this will cancel, so you'll get a 2. Okay. So next thing we want to do is over here, we get y is equal to 1 plus 2 cosine of 2 pi over 3 plus 2 n pi. So this will be the same as 1 plus 2 cosine of the reference angle for this. The reference angle for this is pi over 3. And I'm sorry, no, it will be 2 pi with not the reference angle, 2 pi over 3 because 2 n pi will just wrap around and come back there. So if it's here, this is 2 pi over 3. So if you go around and come back, you added 2 pi, it's the same position, so it'll be like finding 2 pi over 3. So we don't need to worry about 2 n pi. Cosine of 2 pi over 3 is minus 1/2. The reference angle is pi over 3, so it's half, but 2 pi over 3 is in the second quadrant, and in the second quadrant cosine is negative since x is negative. So this time we'll get minus 1/2, so we get 2 times negative 1/2. The 2's cancel, you get 1 minus 1 is 0. So the points are pi over 3 plus 2 n pi and 2, y is 2, and 2 pi over 3 plus 2 n pi and 0, and so that would be the answer to that problem. I hope this video helped you with some concepts from section 3.4. If you do your homework, you'll have a better understanding of the material from this section, so make sure you guys do the homework. And don't forget, I told you to derive the formula for cosecant and cotangent for homework, so make sure you guys do that too.